Welcome to this demonstration of network coding as a WiMAX link reliability mechanism. My name is Kerim Fouli. I am at the Network Coding and Reliable Communications group of MIT, directed by Professor Muriel Medar. This work is based on the master thesis of Surat Tirapitayanon and was done with the collaboration of Marie-Josée Montpetit and Xiaomin Shi from our team, as well as Ivan Seska from Rutgers and Abhimanyu Gozin from Raytheon. So here's a brief outline. I shall start with a few motivation slides, followed by the network coding architecture and experiment setup details. Then you'll see me perform the experiment remotely from my laptop. Finally, I'll conclude with a few remarks. So let's start with the motivation. Here's a simplified scenario illustrating the operation of automatic repeat request, ARQ, hybrid ARQ, and a basic network coding scheme. In each of the scenarios, 5 packets are transferred from the base station to a subscriber station. The base station is denoted BS, subscriber station is SS. For the sake of illustration, we assume a fixed packet error pattern. Every third and fifth packet gets corrupted over the channel. That's a 40% loss. Feedback, on the other hand, is assumed not to have any losses. Now with ARQ, each corrupted packet, in this example packet 3 and 5, must be retransmitted individually. A negative acknowledgement must be transmitted upstream. In this example, packet 3 is retransmitted once, whereas packet 5 needs to be retransmitted twice. This creates round-trip time feedback loops, RTT feedback loops. Now HARQ is capable of reducing the number of feedback loops by combining corrupted packets. In this example, the two corrupted copies of packet 5 are combined, which saves one feedback loop and improves both throughput and delay. In the network coding case, what you see is a systematic a priori code where 3 linear combination packets are appended to the block of 5 packets. With the same loss conditions, network coding is able to decode both corrupted packets immediately. This potentially removes all feedback loops. More importantly, rather than having each packet fend for itself, as in HARQ and ARQ, network coding amortizes the cost of redundancy over the whole block. Now let's take a look at the live experimental setup of today. At my group, the network coding group in RLE MIT, we have a web server capable of controlling a WiMAX testbed located at the WinLab in Rutgers University. The WinLab is part of the Genie framework. So from my browser, I will access a web interface that allows me to toggle reliability configurations, run a set of experiments, and view the results. Let me next briefly introduce our implemented network coding architecture. This figure shows the communications layers involved. This is the transmitter, and this is the receiver. Our initial goal was to implement network coding at the MAC or convergence layers. However, since we were running our experiments using commercial equipment, that proved to be a challenge. Instead, we ended up implementing network coding at the application layer in user space. So at the base station, packets are generated at the application layer by a performance measuring application such as iPerf or UFTP. More detail on that later. At the IP layer, they are filtered using NetFilter and sent to the encoder process. Once the coding is done, packets are re-injected into the IP layer, where they are transmitted across the WiMAX stack to the receiver. At the receiver, they are similarly extracted at the IP layer by NetFilter for decoding. Note that when network coding is used, ARQ and HARQ in the WiMAX stack are turned off. Let's take a quick look at the implemented encoding process. We choose to implement a simple intraflow block encoding algorithm. This is illustrated in the 6 steps shown here. In the first 2 steps, buffering and concatenation, IP packets are buffered and concatenated until a size or a time threshold is reached. Then in steps 3 and 4, padding and segmentation are performed so as to produce 1400 byte packets. These packets or segments are either sent to the IP layer uncoded, or, in the case of redundancy packets, linearly combined. Linearly combined as shown in step 5. Now, if coding is performed, a final encapsulation phase ensures that the coding coefficients and the block ID are appended. They are required for decoding. So the network coding algorithm first sends the systematic packets, then transmits a number of redundancy packets that are coded. The only variable parameter in our experiment is the redundancy factor, which is the percentage of coded packets sent with each block. This parameter varies from 0 to 100%. Now the block size is 120 packets, so a redundancy factor of 10%, for example, means we're sending 12 additional coded packets. The field size is 2 to the 8, so our coding symbols are bytes. Let's move on to the experimental setup now. This figure shows the experiment setup. So this is a downlink transmission from the base station to WiMAX subscriber station. The power and modulation coding scheme, MCS, are fixed so as to generate a certain level of packet loss. In the downstream, a 64 QAM at rate 5/6 is selected, whereas in the uplink QPSK 1/2 is used. Our interface allows for 5 reliability configurations, but today we'll focus on 3 of them. The raw configuration has no reliability, chase combining HARQ, and network coding. We will run several network coded configurations, each having a different redundancy parameter. 2 types of experiments will be run, as shown in the figure also. First, an iperf stream is generated to evaluate the throughput and loss. And second, a UFTP file transfer is executed to compute the file transfer delay. Both iperf and UFTP will run at the application layer and use UDP. UFTP is for UDP FTP actually. The offered load in both cases is 6 megabit per second. And iperf will run a 30-second stream, whereas UFTP will download a 10 megabyte file. And finally, it's important to mention that the default ARQ and HARQ settings are really employed in our experiment, so these are default settings. This table shows the main MAC and physical layer settings. You can see the number of retransmissions for HARQ, for example, that's 4. Now the transmit power selected is 21 dBm. And that's it. We're ready to go to the live experiment. So let's go to the web-based tool. Here we are. Now the home page and setup pages are descriptive material. We describe the project, experimental setup. The read interface is at the experiment tab, where we can select the experiment type and reliability configuration using these buttons. The right panel contains scripts, commands, and outputs for debugging, and the 2 indicators on the upper right corner show the status of the base station and subscriber station. As you can see, the setup scripts have already been run. This is a remnant of one of the setup scripts. The results tab over here will list the throughput, the loss. If you click here, the file transfer delay results in table format, but also in histogram format. Now let's launch a throughput experiment with no reliability measure, that is in raw configuration. So each experiment takes 3 to 5 minutes. So I hope you don't mind me fast forwarding to the results section at each time. The results appear automatically, and here we go. So for this experiment, the throughput was 385 megabits per second out of the 6 megabits per second that were offered. So that's the loss percentage, 35%, calculated, of course, at the application layer. Let's look into the scripts to check out the physical layer parameters. RSSI was minus 71 dBm, and CINR was 20 dB for this experiment. Great. So let's move on to testing HERQ. Here we are. So the throughput for HERQ is 328 megabit per second. That is slightly less than the 385 you got with raw configuration. The losses are 44%. Now HERQ achieves less than the raw configuration, but that's a misleading statement since HERQ represents reliable throughput, whereas the raw throughput is inherently unreliable. In addition, HERQ, by attempting to transmit each and every packet reliably, is incurring more complexity. Let's continue to see what network coding does. We'll start with a redundancy of 10%. And the results are in for network coding with 10% redundancy. So as you can see, the throughput is lower at 2.66 megabit per second out of the 6 megabit per second offered, and the loss is 54%. I'm going to now run a series of experiments with network coding with different redundancy percentages, and I'll look at the results together. This result is quite representative of what happens in most of our experiments. So as the redundancy factor increases, the throughput is going to increase until it reaches a maximum very close to the total offered load, in this case 5.6 megabit per second out of the 6 megabit per second. Very low losses in here, and this corresponds to about 40% of redundancy. After that, In most of the cases, in most of our experiments, the throughput remains around this area even though we increase the redundancy until 100%. So like HARQ, network coding does provide reliable throughput, but it does do it more efficiently in this setup, despite running from the application layer. Let's look at some file transfer experiments. Now this is the result for the raw configuration in a file transfer. The time it takes is 28 seconds to transfer a file of 10 megabytes. Note that UFTP, the application layer performance measurement tool, runs on UDP and has its own reliability mechanism embedded in. That explains the ability of UFTP to transfer files over this raw configuration. HERQ has a significantly higher transfer delay than the raw configuration. The delay here is 37 seconds versus 28 seconds. In addition to the queuing and processing complexity, HERQ also incurs more overhead, with redundancy going up to 400% potentially. Let's move on to network coding and see how that fares. This completes the set for the network coding experiments. So as expected with low redundancy factors, network coding has high transfer delays. Goes up here to 60 seconds, nearly 60 seconds. As redundancy increases, network coding outperforms the other schemes very clearly. Reduces the transfer delay. At 30% it's reduced to about 15 seconds and then remains at about 15 seconds thereafter. There is no significant change for higher redundancy factors. So the sweet spot here would be around 30% redundancy. It's interesting to note that the optimal redundancy for file transfer delay is different than that of throughput. Finally, a few conclusive remarks. The experiments show the viability of network coding, although it was run at the application layer. It does show significant gains over HARQ. This demo was presented at MACOM 2012. Please take a look at the archive article, which has deeper discussion of different reliability schemes. It has a pretty large literature review, some multi-thread design over there, and also much more detailed algorithms and parameters. In future work, we'll look at, of course, MAC layer implementations, speedier, dynamic redundancy levels, being able to change the reliability factor dynamically using feedback. We look at Wi-Fi implementations, very important field. And of course, we look at some unique features of network coding, such as multiple hop scenarios and the use of recoding, multipath combination scenarios, which are very easy using network coding. So network coding does show great promise, different 4G technologies. It does simplify the MAC layer, and it has potential to boost performance. We have implemented it at the application layer, so that shows that it can be implemented over the top as an evolutionary low-cost upgrade. but naturally going into the kernel and into the layers will provide more speed. Thank you very much for watching this demo, and please do not hesitate to contact me at that email or else through Professor Muriel Madar. Thank you very much.